Um, okay. Hello, everybody. Thanks for coming to my talk, which is today about some of the virtualization technologies which have been around for quite some time. But specifically, we'll look at how Windows operationalizes many of them for security purposes. So a bit about me, I work at a security startup called Prelude, and I'm just interested in really anything related to Windows internals, C assembly, anything of the sort, and I like to blog about that stuff. So a bit about the agenda today. We'll first go over legacy exploits and techniques. Then we'll go into another security boundary being implemented on Windows, the reasons for that being based off of those exploits and techniques. And then specifically, we'll get into some of the actual security features which are built on top of that additional security boundary. So kernel exploitation, it's fairly old. It may seem something that's pretty niche. At one point, maybe the topic, it wasn't as well documented, but to date, there are just so many available on the internet for free, talks, articles, POCs, that sort of thing. And vulnerabilities in kernel mode reside in multiple components. A couple of the popular ones are I/O handlers. This is typically what we see in third-party vulnerable driver exploitation. But it can be also found in native OS components, anything that processes untrusted user input, so system call interfaces, network components, etc. And with legacy exploitation, things were just insane at the time, right? The entirety of the pool address space on Windows was executable. There's no real enforcement of execution environment at the time. There's little address space randomization, and in cases where there is, the entropy is not very great. There's no control flow validation, right? If we have a function call that we want to make, and that function call's address is computed at runtime, is there any guarantee that what we're calling into is a legitimate call target? And there's no enforcement of memory permission boundaries, right? What's stopping an attacker that has access to the kernel from just directly manipulating memory? The reason why things were so crazy at the time is it turns out defending kernel mode is very difficult. When you have a user mode mitigation, such as data execution prevention, that can be enforced by the user kernel security boundary. So what I mean by that is an attacker can circumvent DEP by calling into something like virtual protect to say, hey, I'd like to mark this memory that was once writable as executable. But you've got to ask the kernel to do that for you. So you need some kind of execution primitive in order to make that happen. Well, kernel mode is a different story, because if an attacker is able to read and write into the kernel, there's no additional person that needs to be asked in order to manipulate that memory. The page tables are directly managed by NT. And because of that, an attacker with kernel mode can just directly manipulate memory without an execution primitive. So this is obviously an issue. So the first attempts at this was a hardware-based protection known as supervisor mode execution prevention, or SMEP. And effectively, it's a CPU mitigation that enforces one of those bullet points I mentioned earlier, which is execution environment. And the reason for this is because the common technique at the time is to do something as follows. An attacker with a kernel vulnerability allocates some kind of shellcode in user mode, right? They're operating in user mode. They want to escalate privileges to kernel mode. Well, they allocate some sort of shellcode in user mode that's going to be executed in context of the kernel. And then what happens, is a kernel vulnerability is used to corrupt some sort of function pointer or pointer, what have you, in the kernel. That's corrupted with the address of that allocation. So what happens when that address is called, instead of calling into the original call target, we call into user mode. Well, that call is made in context of the kernel, and so that shellcode residing in user mode has access to privileged instructions, address space, etc. Here's a diagram of how this looks, expertly made in draw.io. So we have a function pointer array here. The second index is overwritten with the user mode address, and we can see that redirection will go into user mode by invoking that specific index in kernel mode. So the way that SMEP works is it looks to say, hey, anytime the CPU it's operating in kernel mode, the current privilege level of the CPU's code segment is kernel mode. If we're touching a user mode address, that's bad. Blow up the machine effectively. So that would mitigate the previous scenario, except for a couple fundamental issues. And namely, the source of truth for SMEP is in the page table entries for a given memory address. A page table entry describes, hey, this memory region or this memory page is, writable, it's executable, it's read-only, those sort of things. And it also denotes the physical frame backing the address, which we'll talk about in a little bit. So the source of truth for SMEP is located in kernel mode. And there's a special bit in that page table entry I just mentioned that's known as the user supervisor bit. If the user bit is set, well, obviously the CPU is going to treat this as what? A user mode page. If it's set to supervisor, it's going to be treated as kernel mode. So what's stopping an attacker from flipping that bit from user mode, as the user mode page is allocated as, to something like a supervisor page? Well, when the CPU goes to do the check, it's going to see that that user mode bit is set to supervisor, and it's going to let execution go through. So we can see that SMEP is an improvement, but it's not robust. And it all boils down to this. If you have a kernel mode mitigation that's defending against a kernel mode attacker, and your source of truth for that mitigation is also in the kernel is now defending against itself, right? What's stopping an attacker from corrupting the user supervisor bit before doing their execution? What's stopping an attacker from turning off or disabling the kernel mitigation before doing their attack? So the answer to this question is we need a higher trusted entity than the kernel. As we saw before, what does user mode have to do to get around DEP? You've got to ask the kernel. We need a similar thing here. And the way this is instrumented is through something called virtual trust levels. So Microsoft very cleverly uses the existing virtualization technologies to create a higher security boundary. So we've all heard of virtual machines before. We've heard of virtual machine isolation. To someone that's just looking at it from the outside, it may seem that there's these crazy security features that go into not allowing these VMs to, talk to one another, et cetera. But it really comes down to one thing, and that's how the hypervisor can fundamentally configure memory. So what happens is the hypervisor, in this case Hyper-V on Windows, can partition a virtual machine in its own physical address space and make that memory only valid in context of that VM. And that technology is known as second layer address translation, or SLAT. But in order to dive deeper into that, let's take 1 second to talk about virtual memory in general and how the user mode address space isolation works on Windows. So modern OSs, they implement virtual memory, which effectively is an OS-created abstraction that allows the operating system to work under the illusion that much more memory is available to it than is actually physically installed, right? If we have 16 gigabytes of physically installed memory, we'd like the OS to not be limited to that. And the way that works is memory contents can be flushed out to disk when not in use, freeing up physical memory. But the way that that actually works, all that memory is tracked virtual to physical, is through something known as the page tables. And specifically, page tables contain what? Page table entries, which we've already mentioned. Page table entries denote properties of the memory. Is it readable, writable, executable? And also, as I mentioned, the physical address backing that virtual page. So consider just a simple operation, such as a write operation to a virtual memory address. Well, if we know that virtual address is a OS-created abstraction, we know that that content of that write has to be committed to physical memory eventually. And because of that, what happens is when the memory manager unit portion of the CPU accesses a virtual address, which is what the CPU acts on, it has to first translate the virtual address into a physical address. And there's a cache, which I'm not going to talk about here. But the gist is, if you look in the image here, you have a virtual address in the top left corner. This goes through a series of page tables. On long page mode on 64-bit systems, there's typically 4. And that virtual address is actually used as like a key or an index in order to tell the MMU, hey, you need to access these very specific indexes in these page tables, and eventually you'll find your final physical address. So in comes a virtual address, goes through the page tables, out comes a physical address. Now you may be wondering, why is that relevant? Well, the user mode address space isolation on Windows is facilitated using the page tables. So each process gets its own set of page tables. And when the CPU is executing in context of a given process, the per process page tables are loaded into a special CPU register, and that's used as the initial base to determine where the mappings are. So if you look on the left-hand side of the screen, although it's very small, we have services.exe. And a virtual address in here, it translates to a physical address. But what happens when we go to search indexer.exe and use the same virtual address and try to map it. We see that Winbag says that the translation fails. Why? The mappings for services.exe's page tables are not the same as search indexer's page tables, and so the memory is not even valid in context of that other process. So the analogy I'm trying to draw here is that just as we have per process page tables that give us the user mode address space isolation, we now can use per VM page tables, which give us VM address space isolation. And these second set of page tables are known as the extended page tables. And the reason for this being is if you look in the image here, virtual machine 2 accesses a virtual address, but it's a VM, right? It doesn't know it's running on a physical machine with other VMs running. So when it goes to work on memory, it just operates on memory as if it's a normal computer. So a physical address eventually gets emitted, right? It's working on virtual addresses, goes to physical. But that physical address it accesses isn't necessarily indicative of the actual system physical memory. So what happens is VM2 accesses physical address 1000, but that's really located at, let's say, 4000 on the physical machine. So something's got to compensate for that, and that's exactly what the extended page tables do. It takes the physical addresses, which are intermediary guest physical addresses, and converts them into system physical memory. And each VM has a set of those extended page tables. So here is a diagram of how this looks. VM1, as an example in the top left, accesses a virtual address. It gets converted into a physical address. But that physical address is only valid in context of that VM. The extended page tables for that VM are loaded into a special CPU register from a per VM control structure called the virtual machine control structure. And that contains the necessary information to get the final physical address. So back to our original point, how do hypervisors prevent memory from being accessed in one region to another? All of this is the same technology which facilitates virtualization-based security, or VBS, on Windows. VBS is a special mode which instruments virtual trust levels, which really act as a VM in the sense of it's not a VM because there's virtualization of like the network stack or disk I/O, anything like that, but each VTL is treated as an isolated physical address space, just like a VM is. And we have two main ones. We have VTL1, which is secure mode, and VTL0, which is normal world. That's what typical users operate in. Secure world has secure kernel and the isolated user mode, which we'll talk about a little bit later. And VTL0 contains a typical NT user mode setup. And here's a diagram of how this looks. So VTL1 and VTL0, they're treated as our VMs. So what does that infer? They both have a set of extended page tables associated with them, just like any two VMs would. But all of the extended page tables in each VTL are actually mapped to the physical frames on the machine. So what I mean by that is earlier we saw an example where physical address 1000 in the VM was really 4000. Well, in context of VBS, physical address 1000 is still mapped to real physical address 1000. So you may be wondering, Connor, this sounds dumb. Why do we have these extended page tables if they just forward on to regular memory? Well, what are page tables made up of? They're made up of page table entries, which denote properties of memory, such as readable, writable, executable. VBS is used to configure two different access rights on physical memory using the extended page tables through those extended page table entries. And here's how this actually works. So you have VTL1. That's the address space treated as secure world. And because it's treated as secure world, it can actually impose its will on VTL0. So when the machine is booting, VTL1 is actually allowed to configure all of the page tables for VTL0 as it sees fit. And it does that by asking the hypervisor to do so through an interface called a hypercall, which is similar to a system call, but it allows a guest to interface with its host hypervisor. So if VTL1 is allowed to configure all of the extended page tables for VTL0, that infers it can configure those extended page table entries. So it's allowed to actually configure VTL0's memory to say memory is readable, writable, etc. And VTL0 is what traditional users operate in. And what's beautiful about this is that the extended page tables are not located in the kernel, just like the traditional page tables. They're managed by the hypervisor. So in this case, if you want to corrupt those extended page tables or manipulate them, you have to ask a higher security boundary to do so, which is exactly what we saw with DEP. User mode attacker has to ask the kernel. Now the kernel has to ask the hypervisor. And all of this is the basis for VBS and the features which I'm going to be speaking about. So here's a quick example of the first feature which I'll talk about, which is HVCI, hypervisor protected code integrity. This is write XOR execute on Windows in the kernel. So what that means is memory can never be both writable and executable at the same time. So if you know anything about process injection, you know typically the way it works is you allocate some memory, you write some shellcode there, and you execute it. Well, you allocated memory and you had to write your shellcode there. So your shellcode had to be writable, your memory region, and then you had to execute it. So you needed execute permissions. HVCI never allows that scenario to occur by instrumenting all of the VTL0 extended page tables never to contain both the write and the execute bit at the same time. So what does this mean for a situation like we saw earlier, where an attacker can corrupt a page table entry to mark the user bit as supervisor? In this case, marking the execute bit as cleared, allowing execution to happen. Well, what would happen is the CPU would access that memory to execute it, and it would say, hey, this PTE, this page table entry, it says it's executable. Great. Well, with VBS running, this means SLAT is present. And that means that address being accessed by the CPU is treated as a guest page, just like a typical virtual machine. And because of that, we need to fetch the extended page table entry corresponding to that page. Well, HVCI says there will never be an extended page table entry which contains both the write and the execute bit. So it does a comparison. It says, hey, I see this PTE from kernel mode has the write and execute bit set, but my extended page table entry, which is now the new source of truth managed by the hypervisor, doesn't. And because there's a mismatch, execution is never allowed to occur. And what this basically means is it's effectively impossible to create unsigned code execution with HVCI enabled just with a kernel mode read-write vulnerability, whereas in the past it was. So where this all comes together is in the bottom image here. You have PTE, which is a standard page table entry, and EPTE, which is the extended page table entry. You can see the PTE has a red E, which is representative of an attacker corrupting maliciously a page table entry which was not originally executable to executable. But we can see the extended page table entry was not also corrupted. Why? Because it's managed by the hypervisor, and you need a way to access the hypervisor in order to also do that. And because of that, when this function is called and the shellcode is executed, we'll get a blue screen. Why? Because we're trying to execute memory, which even though the traditional page table says is executable, is not actually executable because the extended page table entries say so. And just briefly before moving on, VTL communication channels. So VTL0, which is traditional, user kernel, still needs to request sometimes the services of VTL1. This is for things like, hey, VTL1, I need to let you know about this state change, as an example. So there's a mechanism known as a secure system call, which is emitted as a VM call opcode, which is just a hypercall. And just like a traditional system call, you load up a secure system call number. That gets passed to a dispatch function in secure kernel. Secure kernel parses that number, parses the arguments safely, copies them, and then performs the action. And here's what this dispatch function looks like in secure kernel. It's just a big switch case, each case representing a secure system call number, and the various dispatch function being available. So now that we've talked about all that, what are some of the features that Microsoft actually builds off of virtualization-based security? The first was HVCI, which we just talked about. I'd like to talk about some of the other ones now. So the first one that I'd like to talk about is something known as kernel data protection. There's a Microsoft blog by my friend Andrea, which goes over static KDP, which is the first one we'll talk about. And what this basically is an interface for kernel developers to guarantee read-only memory as read-only. And how it works is it implements a read-only SLAT entry in the VTL0 extended page table entries. So again, we just saw the previous example where we could corrupt a page table entry to corrupt the metadata and trick the CPU into executing memory, etc. Well, if you have memory that's read-only, that you want to guarantee to be read-only, You can call this function, and then even if the regular page table entry is corrupted to say, hey, this read-only address is now read-write, the extended page table entry enforces no that it's not, and it guarantees it by the hypervisor to be read-only. A good example of this being used is already in Windows. It's in the latest version of Windows. There's a famous bit mask called GCI options and ci.dlo, which is a state time management bit mask of effectively the code signing policies on Windows. One of those bits corresponds to driver signing requirements. So attackers will use some kind of primitive to corrupt that bit mask to disable all kernel driving signing requirements and be able to load unsigned drivers. Well, that bit mask now has a slat entry which says it's guaranteed to be read-only. So the old primitive attackers used to corrupt the page table entry to mark it as read-write is now obsolete because it's managed by the hypervisor. There's also dynamic KDP, which I won't spend too much time on. My friend Jordan has a very good blog on it. But effectively, it's the same thing, but instead of static memory being marked as read-only, you can do it with dynamic memory. And the reason why this is its own feature is because pool memory is a little bit different because it's constantly allocated, freed, the states. It's a difficult problem. And so there's a little bit of nuance here, but you get the point. You can basically have dynamic memory also guaranteed as read-only. Kernel control flow guard. Many of you have probably heard of control flow guard. It's actually fairly old at this point. It was shipped as optionals in Windows 8.1. And effectively what happens is it prevents indirect function calls. So an indirect function call is basically a call that happens to a target that was computed at runtime, so through a register or a pointer. And what happens is Windows, instead of directly calling into an indirect target, will actually say, hey, hold on, before we make this call, I have this source of truth over here called the kernel control flow guard bitmap. It knows about all of the calls that should actually be used in those legitimate function calls. Let me check if this call that I'm about to make is known in this bitmap. And if it is known, hey, I knew about this function at compile time, I'll allow this call to occur. If it wasn't known, it infers that someone dynamically corrupted this function pointer and we should disable execution. Well, if you just listen to my spiel there, what's the choke point there? It's the bitmap, right? Because the bitmap is the source of truth. Well, if you have kernel control flow guard and you're defending against a kernel attacker and your bitmap is also in kernel mode, what's stopping an attacker from just corrupting that bitmap, marking all memory as valid call targets, and then making their function call? Nothing. And that's why HVCI is actually needed. The feature won't be fully instrumented without it in order for kernel control flow guard to actually be enabled. And the way that that works is similar to KDP. There's a read-only extended page table entry put on the bitmap that makes it incorruptible from VTL0. And here's a little more context to go along with this. This is a Winbag screenshot I took of a little demonstration. I took the address of the bitmap, and I corrupted the page table entry, which is managed by the kernel, to make it kernel, write, and valid. So if you look in that PTE dump, you see, G-DA-KW-V. K is for kernel, W is for writable, V is for valid. Well, when I actually use the EP command to write data there, I get a memory access error. Why? The extended page table entry does not say that this is writable. So when I try to write it, it denies me. And you now need a hypervisor vulnerability in order to mark the kernel control flow guard bitmap as writable. Kernel CET. Kernel CET is kind of the counterpart to kernel control flow guard. CET actually contains two features. Windows only instruments one, which is the shadow stacks. Indirect branch tracking is similar to control flow guard, which Microsoft just uses their implementation. And it works off of a shadow stack being created of the stack computed. And so all of the return addresses are stored on an immutable, hardware accessible only shadow stack. So if you do a ROT-based attack, for instance, or you corrupt a return address, so if we've all heard the typical 32-bit stack buffer overflow where you override a return address, well, those return addresses are actually protected now by the shadow stack. So when you corrupt a return address and perform the ret, well, that ret kicks off a check between the shadow stack and the legitimate stack. If they mismatch, you know that someone's corrupted it and you crash the process or the machine. As I mentioned, it's a hardware mitigation, but it relies on VTL1. So shadow stacks still have to be allocated from software, right? There's a region of memory known as the MIVA kernel shadow stacks region. That's where shadow stacks are allocated from. Well, if you allocate your shadow stacks from VTL0, you need to somehow protect them. And that's exactly what happens with CET enabled. With CET enabled, as part of the allocation routine, those shadow stacks are marked as read-only in VTL0, so they cannot be corrupted. And what this basically does is it delegates all manipulation of the shadow stack for legitimate reasons like long jump or thread context update. Only hardware or VTL1 should ever manipulate the shadow stack. And that's exactly what we want because it's a higher security boundary. So PatchGuard, you may have heard of it before. There's something called Secure Kernel PatchGuard or HyperGuard. I'll be referring to it as HyperGuard. And it addresses some of the shortcomings of PatchGuard. So PatchGuard, again, is a runtime checking kind of mitigation in Windows. But again, it runs into the same thing where PatchGuard is kernel code trying to defend against kernel modifications. Secure Kernel PatchGuard or HyperGuard can build on top of that, can do some of the same things like check things of interest like MSRs, control registers, etc. But it can actually intercept access to those using the hypervisor. So there's something known as Secure Kernel PatchGuard Extents. I know I just said I'll refer to it as HyperGuard, but I forgot all the acronyms are SKPG. And these extents define a region of memory that you care about. So MSRs, control registers, instructions, etc. And those are registered as intercepts. So those intercepts can actually be used to access, literally intercept access to some of those items of interest. And so this brings us from periodically checking things with PatchGuard to being able to, on the fly, detect things by intercepting them with HyperGuard. And my friend Jordan has a multi-part blog series on that. Of course she does. You also have Credential Guard. I like the word guard being used so much. I actually like it a lot. So this is a Windows enterprise specific mitigation. And if you've ever heard of traditional credential dumping, which I'm sure most of us have, being the conference that we're at, it's because you eventually invoke some kind of read process memory call, typically speaking. There are other ways, obviously, to get the credential material, but your typical dumping is because you're reading the memory space of LSASS, which contains credential material. Well, all the credential material from LSASS is now actually protected by the hypervisor. And so traditional LSASS dumping becomes obsolete with this mitigation enabled because of the fact that even if you can dump the address space of LSASS, you're not going to find credential material in there. And this goes for Kerberos TGTs as well. In my red teaming days, one thing that I like to do is do the TGT delegation trick, which is fairly old. And basically, if you don't have a password, you just ask the domain controller, hey, give me my TGT, and use that to authenticate around the domain. Well, that stores your TGT locally on that machine. Well, that's no longer available for you. And so if you try to use that trick with Credential Guard enabled, it won't work. Same with TGT dumping on other cached TGTs. There's also something called VBS enclaves. And this is really cool because VBS enclaves are just now becoming available to third-party developers, as far as I'm aware, on Windows. And it's an isolated region of memory which is protected by VBS. And so what this basically means is that developers can isolate sensitive portions of their application which are not even accessible by kernel mode of VTL0. And enclaves usually, generally speaking, are manifest as DLLs, and these DLLs basically get loaded into this container process. And that DLL is the enclave region. And it, as I mentioned, cannot even be accessed by kernel mode of VTL0. And enclaves also have a limited API set, so it's not as simple, and you can also read this on Microsoft documentation. It's not as simple as just ripping out everything and putting it in your enclave, because you're not going to have the same functionality. But it gives developers an interface now to seal sensitive data, which is guaranteed by this virtual secure mode, which we've talked about. So what's the conclusion here? Well, it's self-evident that Microsoft, they've made heavy investments into features and protections with very strong guarantees, right? We saw as a concrete example like the kernel control flow guard bitmap. Not even a kernel mode attacker can make that bitmap writable. So it's made some techniques and procedures which were used for a long time, like page table entry corruption, just outright obsolete in many cases. And these are features which you don't need some kind of special licensing to do this and that. Anyone can turn on memory integrity, which is HVCI on Windows. These are baked into the OS, ready for everyone to use, and I would highly recommend others to use them. We think about them as these cool features, but they're practical. They can be used. Most of these features are obviously dependent on VBS. All of them are actually. But it's interesting to take a look at what will happen in the future with some of these other mitigations like kernel shadow stacks, which are not fully available right now because you need specific hardware and because it relies on VTL1. So just as attackers changed from the DEP and ASLR days, going from stack-based buffer overflows to doing other things, other primitives, which force them to adapt. It'll be interesting to see how, when this technology becomes more and more adopted, how attackers adapt. And yeah, I'm definitely not an expert. I can't guarantee to answer every question, but I just want to say thanks for coming to my talk, and what I can answer, I'd be happy to address. So thank you.